The emphasis placed on utilizing data in today's world cannot be understated. Within the realms of business, environmental science, psychology, information sciences, and other disciplines, the gathering and subsequent analysis of collected data allows for the theorization and construction of networks and relationships. The question we intend to answer is how to construct and interpret networks and networks derived from raw data. Now you may be wondering, why would we care about the existence of networks? Studying networks allows us to determine patterns and statistical patterns of network data. This then allows us to render models and designate principles of these networks. From here, we can gain understanding of why networks are organized the way they are and predict behaviors within this network. It should be prefaced, raw data are not necessarily networks. As a matter of fact, raw data are often not networks. This determination must be made prior to network construction. Given that data is a network, how do we construct a network from this raw data? Most of the time, when we create a network, all nodes represent objects of the same type, such as people and social nets, bus stops and route nets, or genes in a gene net. However, multi-partite networks have multiple types of nodes, where edges exclusively go from one type of node to the other. K-partite networks have, as may be inferred by the name, K different types of nodes. These multiple types of nodes allow for unique relationships to be expressed. A practical map showing the relationships between two types of nodes may be exemplified by a network of students to research projects. This type of network has two different types of nodes and may be labeled a two-partite student net. Similarly, a network of three different types of nodes may be dubbed a three-partite network. A hypothetical example of such a network would be one comprised of three node types: actors to movies to movie companies. K-partite networks may be represented through K-partite graphs. Taking the example of the two-partite student net encompassing students and projects, we may illustrate this with a graph of two different types of nodes. Edges linking nodes indicate that a particular student works on a specific research paper. This graph illustrates two projections of student project networks. 1. Students are linked if they work together in one or more projects, and 2. Research projects are linked if one or more students work on both projects. The number of projects that two students work on together is equivalent to the number of paths of link 2 connecting these students in the bipartite network. A rule of thumb is that K-partite networks have K one-mode network projections, which is intuitive in that each entity comprised of a single type of node can be described with its own unique projection. In this example, one-mode student projection of a bipartite student project network, there exists three nodes connected to form a triangle. This implies that any two students within the triangle work on a different project, or that three students within the triangle work on a shared project. However, it's not possible to tell the information from this one-mode network projection alone, due to the reality that one-mode network projections do disregard some information. We may construct an incidence matrix A of the student project net to help create a student project matrix. For a particular student and particular project, the value within the matrix is 1 if a student works on the project and 0 if the student does not work on this project. The incidence matrix for the student project net may be represented with dimensions n times m, where n is the number of students and m is the number of projects. Because the contents of the table for a given student and project pair is either 1 or 0, and the total number of students is not equal to the total number of projects, we may describe this specific incidence matrix as a binary non-symmetric matrix. Extrapolating an incidence matrix allows for the construction of K-weighted one-mode network projections. Taking the incidence matrix A from above, we can construct two weighted networks: a weighted student network B and a weighted project network C. The number of paths of length 2 connecting two students, designated I and J, in the bipartite network may be described as this equation. The number of paths of length 2 connecting two projects, designated K and L, in the bipartite network may be described with this equation. Once these are derived, we may then apply a node similarity measure to B and D to construct network projections. The two node similarity measures described here are the common neighbors and the Jacquard index. The common neighbors is the number of shared neighbors of nodes. This measure, when applied to the student network found, supposes that students I and J are linked if they work together in R or more projects, translating to this equation. Similarly, when applied to the project network found, K and L are linked if R or more students work on both projects, which may be described with this equation. The Jacquard index is similar to common neighbors with a twist. There exists a penalty for non-shared neighbors. The index is the ratio of shared neighbors in the complete set of neighbors for two nodes. In the student network example, this may be articulated that students I and J are linked if they work together in at least P fraction of their projects, formulated here. In the project network example, K and L are linked if at least P fraction of their students work on both projects, formalized here. Consider the human disease net, which is modeled here as a disease gene network. One key attribute that makes this network difficult to analyze is the presence of cliques within this network. We have a tool to help us out: graph contraction, which allows us to go from complex to complexant. To perform this, we aim to contract the graph into a smaller graph, ideally a constant fraction smaller. This may be performed via recursion. This algorithm is performed by selecting a node partitioning of an input graph G to guide the contraction. These partitions are disjoint, include all nodes in G, and is either a clique of nodes, two connected nodes, or a single node. These partitions are then contracted into a single node, called a supernode. We then drop edges internal to a partition before rerouting the cross edges between components to corresponding supernodes. G is then set to be this contracted graph. The process is repeated until the graph G is contracted down to a single node. A K nearest neighbor graph of a set of objects V is a directed graph with vertices set V. Edges from each V are drawn from its K most similar objects in V under a similarity measure. This operation has applications within recommender systems, document retrieval systems, problems within clustering, visualization, information retrieval, data mining, manifold learning, and so on. K and Gs allow us to use the network methods on datasets with no explicit graph structure. For example, K and NG can be used to visualize large, high-dimensional data in 2D space. Traditionally, we would have had to compute similarities between objects before projecting these objects into a 2D space by preserving these similarities. K and NG can substantially reduce computational costs, assuming the correct approach. There are two approaches which we can cover for K and NG: brute force and NN descent. Brute force is performed by computing operations for every possible pair of node and edge. The computational cost of brute force is O of n squared, which unfortunately makes it not scalable nor efficient, and due to the specific heuristics required, not general, NN descent is far more efficient. That approximates K and NG construction with an arbitrary similarity measure. The key principle of NN descent is that a neighbor of a neighbor is also likely to be a neighbor. To implement this, start with an approximation of the K and NG, B, and then improve B by exploring each point's neighbors, stopping when no improvement can be made. The accuracy of K and NG constructors may be measured by recall. The recall of one object is the number of true K and N members found divided by K. The recall of an approximate K and NG is the average recall of all objects. The computational costs may be measured through the number of similarity evaluations performed. We observe similar performance in terms of recall and scan rate on different datasets. These datasets may vary widely in terms of number of objects and dimensions. As the dataset grows, there is only a minor decline in recall. Networks represent dependencies among objects, be it co-authorships between scientists, friendships between people, who eats whom in food webs, bonds between molecule resides. Indirect dependencies occur because of transitive effects of correlation. The issue we must address is how to separate direct dependencies from indirect ones. Let's take care of a co-authorship net between scientists, and let's aim to distinguish strong and weak collaborations between scientists. Collaboration tie strengths depend on publication details, such as the number of pages each pair of scientists has collaborated on, and the number of co-authorships on each of the papers. These tie strengths are relevant for recommending friends and colleagues, recognizing conflicts of interests, and evaluating authors' contributions to teams. Now, the observed network depicts combined direct and indirect effects, while the true network depicts only direct effects. These indirect edges on the observed network might be due to higher order interactions. Each edge might contain both direct and indirect components. To deconvolute this observed network, we must reverse the effect of transitive information flow across all indirect paths. The challenge of this is that direct edges in a network can lead to indirect relationships. This is also known as transitive information flow. To deconvolute a network, we use a closed form expression for G observations to recover true direct network G direct. Transitive closure as a closed form may be described with this equation. Knowing this, we then aim to efficiently calculate G direct. We do this with the eigen decomposition principle. To perform this, we express G observations by decomposition into eigenvectors and eigenvalues. We then form a diagonal matrix such that this is the case. From here, we recover the true direct network as this. Running this back to the example of distinguishing strong and weak collaborations between scientists, we construct a net using the dataset holding the unweighted network of scientists working in the field of network science. Two authors are linked if they co-authored at least one paper. Applying network deconvolution here yields a weighted network whose transitive closure most closely captures the input network and where the weights represent the inferred structure of direct interactions. True collaboration strengths are found by summing the number of co-authored papers and downweighting each paper by the number of additional co-authors. Remember the Jacquard index. The ground truth data includes these true collaboration strengths and the correlation found between network convolution assigned weights and true collaboration strengths. Network deconvolution predicts collaboration tie strengths solely by using network topology, which does not use other publication details. Network deconvolution removes spurious edges due to indirect effects, decreases overestimated edge weights, and rescales edge weights so that they correspond to direct dependencies between objects. Simply put, network deconvolution makes for a better network.